So hi everyone. As Laura mentioned, I'm a computational journalist. So that means I do two things: apply data science to journalism problems, and try to do journalism about the use of computation in society. And that's what this talk today is about. Scoping this talk is really hard. So the talk we're going to have right now is actually brutally narrow. This is one taxonomy of the possible harms from technology that I like. This is from the Institute for the Future's Ethical OS. And they talk about these various places where technology can have negative unintended consequences. And we're just going to talk about one place where this is possible, right? This machine ethics and algorithmic biases portion. And in fact, I'm going to talk about an even narrower part of that one category, which is allocative fairness. So the setting here is that we are allocating some reward or punishment. So you get into a school, you go to jail, something like this, which is not given out to everybody. And we've decided that the way that we're going to do this is we're going to predict something like, will you show up for your trial if we release you? Will you succeed at this company? Will you graduate from school? In particular, this ignores another important category of potential harms called representational harms. So that's more like, if I search for CEO, what is the gender of the pictures I get back? Right? So we're not talking about that. We're talking about this very specific setting. But hopefully, we'll learn some things that can start to be applied more broadly. Now, before I really get into this, I should say that the things that we're going to talk about today are complicated. The stakes are very high. There's a lot of history here. There are a lot of open, both political and philosophical questions. So I don't expect you to agree with everything I'm going to say. In fact, I would be very surprised. I'm going to try to describe the possibilities rather than advocate for particular courses of action. But we are in hotly disputed territory in many cases. So let's start with some sort of intuitions about what fairness might mean in this setting, and then we're going to make this a little more formal, and then we're going to look at some case studies about actual algorithms actually being used. So one way to think about fairness is as allocation across protected classes. So this is it's basically a legal construct. It has a long history. And if you sort of go down this list, you can see that sort of one category after another was gradually protected, right? So all the way up to genetic information, which is it's now illegal to discriminate on the basis of genetic information. And so these are certainly not the only categories of fairness you might care about, but they're a good starting point. If for no other reason than getting this wrong might land you in legal trouble. I want to start introducing the sorts of data that we're going to talk about one little bit at a time. And I'm going to start with this graph, which has only two numbers. This is real data on traffic stops in Massachusetts in 2001. In a minute, I'll explain why that data set. And what do we have here? We have the number of stops of minority drivers and number of stops of white drivers. So when you get raw data, it's going to look like this at first. So is this fair? Are the police pulling over people fairly just based on this? We don't know. Okay, why don't we know? Right, so we're starting to get into building up some intuitions here, right? So we don't know the population of people who live there. In fact, what we want is the population of drivers. The other problem is we don't know if the drivers are doing the same thing between minority and white drivers, right? They live in different places. They're driving on different roads. They're driving different cars. There might be different ages. Who knows, right? There's all these questions about how do we compare these groups. So you can sort of start to tease out some basic questions about what fairness might look like here, right? What baselines do we compare it for, and are we really comparing the same thing in these two groups? And if you start to tease this out a little bit more, you get very quickly to a legal concept, which is the concept of similarly situated. And so this is a key concept in discrimination law. And it says, well, it's not that the man got promoted and the woman didn't, and that's discrimination. It's that they were equally qualified or equally deserving or similarly situated, right? So very early in law, we have this concept of we have to have some idea of comparison and also what is relevant for comparison, which is also part of the disputes around this subject. This is a nice piece of data journalism from a few years ago, looking at sentences given out by Florida judges. So Florida uses this point system that tries to add up sort of criminal history and the severity of the charge, and it sort of gives this rating, and then the judges are supposed to base the length of the sentence or the severity of the sentence based on this rating. And what they found is that for most charges, for people with the same point score, in other words, similarly situated, the black defendants got longer sentences. So most of this talk, by the way, I'm just going to talk about black and white populations. I realize this is a very, there are other races, right? But this is the simplest possible setting that we can start to talk about these problems. So the journalists who produced this analysis knew this, and what they did was they compared people within the same point score bucket. And some of you may recognize that this is sort of a very simple form of controlling for a variable. So when you hear about statistical analyses or regressions, controlling for age, controlling for income, controlling for criminal history, this is what that word means. We're trying to compare people who are similarly situated. Let's look at this graph for a second. This is gender breakdown of major tech companies. This is another type of data that we often use to talk about fairness and discrimination. And what I want to point out is that if you think about this for a minute, you'll see that there's actually a completely different notion of fairness here. In creating an image like this, you are implicitly advocating for a different concept, which also has a legal name and a legal conception, and that is the notion of disparate impact, right? So now we're not talking about, were these two people equally deserving of promotion and one got it and one didn't. Now we're talking about, I don't care how you got to the result. We have way more men than women working in tech, right? It's a different notion of fairness, and it is also a legal standard. To my knowledge, this law here, the 4/5 rule, this is the only place in fairness and discrimination law that a numerical threshold appears, which is interesting, right? Because the courts have been very reluctant to put thresholds on things, except for this one case from 1979 originally. These ideas of, let's call them disparate treatment and disparate impact, are in tension with each other. And this is a graphic you may have seen. And it was endlessly sort of copied and recaptioned and so forth. But this captures the fundamental intuition about these two different types of fairness. Do we want to, give everybody the same treatment no matter where they start from, or do we want to give people different treatment so that they end up in the same place? So already with these very simple examples, we can see that there are different notions of fairness at play, different moral and legal conceptions. And they're not always going to lead to the same outcomes, right? They are in tension with each other in some way. And we're going to get into the mathematics in a second, and you'll see that this problem multiplies. Finally, no algorithmic fairness talk would be complete without looking at the ProPublica Compass story. How many of you are familiar with this? Okay, so most of you, yeah. So big, had a huge effect on this discussion. And what ProPublica argued, the core of their story, as I read it, is that if you are a person and you're not going to commit another crime, your likelihood of being labeled as high risk and therefore potentially being held in jail as opposed to released pre-trial is about double if you are black versus white, right? And so that seems like a very immediate type of unfairness. To get at this, I'm going to sort of jump into the formalisms, and then I'm going to come back out of it at the end and talk about the real world. And there's been a lot of criticism about the way that fairness is researched and taught. Some people saying, if we don't have mathematical definitions of this, how could we possibly talk about algorithmic fairness? And other people saying, well, that fairness isn't a property of algorithms, it's a property of systems in the real world. And I'm sort of ecumenical. I think actually both are right, and we need to understand both. So that's the approach I'm going to try to take today. To get to quantitative notions of fairness, we need to add a few more numbers. So the first thing is, and this is why I use that Massachusetts data, we also have data on not just whether they were given a ticket, but whether they were given a citation. So at that time in Massachusetts, tickets and citations were exactly the same form. You just had one checkbox, and if you checked the box, it was a citation, and it could affect your, you got a ticket, and you could affect your driver's license, and was start legal proceedings. And if you didn't check that box, you got a warning, and basically nothing happened. So that's nice. So we can start to compare a little more generally what happened. And the basic concept I want to say is that there's going to be some decision made by somebody, and we're observing the result. Right? So we start with two groups, and then we add a decision for people in each of those two groups. Then we're going to add one more part. That gets us to 4 numbers. Now we're going up to 8. Now we're going to say, okay, we not only have a decision, we have an outcome. So this is, was the person actually rearrested? This is, did they pass school? Did they end up committing suicide if you're trying to do suicide prevention? Did they succeed at their job by some metrics such as promotions and so forth? So to get to these discussions of algorithmic fairness, we actually have to get up to this 8 variable situation. And what we really have is 2 confusion matrices. I'll show a picture of a confusion matrix in a bit. How many of you are familiar with that terminology, confusion matrix? Okay. So we'll get there. Some notation. I don't expect you to sit here and copy down all the notation and studying it. I'm mostly adding the formulas to this stuff to try to convince you that formal definitions exist, that you can turn these more intuitive concepts into code or analyses of actual code. And so this is a formalization of the allocative fairness setting that we had earlier. So this is the idea. We have some observable features, X. So this could be all your past resume, your criminal history, that sort of thing. We have some protected class, so that, race, gender, whatever it is. We have some decision process which produces an observable score. And normally we say the score is in 0, 1, and then what we do is we apply a threshold. We say if it's greater than something. So if there's greater than, an 80% chance you're going to be arrested, then we're going to call you high risk. So we are turning this into a binary problem. We make one decision, C. And then there's some ground truth, which we call Y. So this is the normal machine learning framework where X is the inputs and Y is the outputs. And this is, all this is we're just assigning symbols to this. Okay? That's all we're doing here. And once you do this, you discover that many, many people have come up with quantitative definitions of fairness. There's a wonderful talk, which I have in the references, called 21 Definitions of Fairness in Their Politics. I'm going to focus today on just a few of them, 4 in particular. You'll notice that many of these have multiple names. And again, don't worry too much about the formalism here. We're going to go through each of these briefly. It's the intuitions that I sort of want you to come away with. So the first one is, hey, let's just not feed race into the algorithm, right? You just shouldn't use it. It doesn't make any sense. It's not fair. Why should the answer depend on race? So what we're saying here is, the formalism just says that the answer is independent of group membership given the features. In other words, if we if I give the algorithm the feature set, and it's going to give the same answer regardless of what the underlying group membership is, right? So this is a starting point, right? This seems like it might be a desirable property. It doesn't really solve the fairness problem on its own, because now what you can do is you can just sort of randomly pick answers, and as long as the answers don't depend on the projected class, it's fair, right? So clearly something is wrong here. We need some other notions. Notice that I did not put predictive accuracy as a fairness criteria, but it is, right? If you're guessing and you always guess wrong, that's a problem. You want to guess as well as you can, perhaps subjects to other things. So ignoring the protected class on its own is not sufficient as a fairness definition. Also, you can't do it. Yeah.
There's another drawback, which is that you can just use the protected attribute might be encoded in X. For example, you use which sorority or fraternity you were in to make a decision about you.
Yes.
And even though I'm conditionally dependent on the attribute given the feature vector, that's a meaningless guarantee in that example.
That is exactly the point I'm about to make. Thank you. So this was a paper on predicting things from your Facebook likes. And so they built this machine learning model, which is actually this like pretty straightforward linear model. And they were able to work out a whole bunch of protected attributes from your Facebook likes. So this is a very general problem. It's actually very hard to hide protected attributes, race, gender, sexual orientation, even political affiliation, religion, all this kind of stuff, or whether you're a drinker. It's hard to scrub this from the input data. It's actually pretty impractical. And we'll look at some other arguments for anti-classification in a minute when we take this to the real world setting. So okay, if that's going to be difficult, what else can we do? Well, we can insist on, let's say, hiring an equal number of men and women. What we're insisting here is that this is called demographic parity. The idea is we don't really care what goes into the machine. We just want the output to match some demographic baseline. Okay, so this is one definition of fairness. This is the definition that is implicitly invoked if you're talking about the demographics of companies' employees, for example. Again, it's sort of an insufficient definition on its own because it says it doesn't matter who we accept as long as we accept the right number in each category. And this, you can tie this to the legal principle of disparate impact, right? This is what the 4/5 rule is demanding. Another definition is called calibration or sufficiency. The way to think of this is this is the sort, or one way to embody the idea of equality of opportunity, or this idea of similarly situated. And what it's saying is that the answer for you should depend only on the things that have relevance to predicting the outcome, right? So we're already in a setting where what we would like to do is make our choice based on some future outcome that we're trying to predict. So if you don't believe that making a choice based on a future outcome is a reasonable thing to do, then this is not the fairness setting for you, right? So we're already working with this idea that if you can predict whether someone's going to be rearrested, if you can predict whether someone will succeed at their job or at school, then what you're trying to do is use that knowledge to make a decision. So this is the version that says, our decision should really just reflect what we think the future outcome should be. And you can show that standard loss functions for machine learning, mean squared error and so forth, will actually produce this. So this you sort of get this for free with most standard formulations of machine learning optimization. And here's what this looks like in reality. I'm sort of jumping ahead a little bit. So here is, again, the ProPublica Compass data. And what we're looking at is for each score, right? This is this rank that they give you, sort of dangerousness 1 to 10. What is the actual probability that someone will be rearrested. And you can see this is on real data, right? So this is the validation data set. This is not the training data set. You can see that you've got this very sort of linear relationship. It's not quite a probability, but you can transform it very easily into an actual probability. And that the variation between black and white defendants is pretty minimal, right? It's all within error bars. And so we say that this is calibrated. In the weather prediction case, we would look at a graph by this and we would say, yeah, when the forecaster says there was a 40% chance of rain, on 40% of those days it actually rained. And then we get to the sort of ProPublica definition. And the ProPublica definition says that we should try to balance the error rates. So now we're talking about the distribution of error as a type of fairness. And this is, you can kind of frame this as a disparate treatment issue, right? So from my point of view as a defendant, I don't care about whether the algorithm is calibrated by some abstract mathematical sense. I care about what is the chance for people like me, who I'm assuming are not going to commit another crime, what is the probability of a positive, right? Am I going to go to jail? So from my point of view as a defendant, this is the number that I care about. Okay, so that's the formalism, right? Again, really, you know, I'm going to put up these slides. You can go through them if you want. There's all kinds of references on this. The only thing I'm trying to convince you is that we can turn these ideas into quantitative conditions, right? So I can look at the data and I can actually say, does it meet this fairness or not, and how close or far am I from this ideal? So how does this happen? How do we get higher error rates for one group? Well, one way that it can happen is the classifier is simply less accurate for minorities because we have less data, right? And it can happen that the most accurate classifier for the majority group is not going to be the same as for the minority group, right? However, even if this is not the case, even if you had balanced input data and as much of it as you wanted, you can still end up with a higher error rate for one class than the other. And this is because all of the fairness definitions that we have talked about so far, well, the three of them anyway, non-anti-classification, can be written as formulas from the confusion matrix. Now, I mentioned this earlier. This is basic analysis of how well we're doing at prediction. And what we're doing is we're just drawing this 2x2 chart for, what did I predict versus what actually happened. And if I predicted yes and it actually was yes, I get a 2 positive. But if I predicted yes and it was no, I get a false positive. And so all these various mathematical definitions, if you look at them for a minute, you can convince yourself that they're all formulas based on these 4 numbers. And these 8 numbers we had at the beginning, right? These are the 8 numbers from the COMPAS data. Those are 2 confusion matrices. Those are confusion matrices for black and white defendants. And there, you can actually see the numbers here, right? These are 2 confusion matrices. So the problem is, because we derive all this stuff from 4 numbers, at least in the binary setting, you can generalize this to continuous settings and so forth. There are algebraic relationships between the quantities. And in particular, there is the tension between disparate treatment and disparate impact shows up in the math, right? And I think everybody has this intuition, right? If the candidate pool between 2 groups does not have equal qualifications, you can either hire everybody who is qualified to a certain point, or you can hire according to demographic targets. You can't have both if the applicant pools are not the same. What is more surprising is that there is a conflict between calibration, so having the prediction mean the same thing regardless of class, and error rates. So again, this is one of those things like I don't expect you to sit here and pick it apart. I just want to show you that this exists, right? So you can do a little math. In fact, you can do it from the definitions on Wikipedia, and you can show that the false positive rate is related to this thing called the positive predictive value, which is what fraction of the people I say are high risk actually get rearrested. And because there is this algebraic relationship, you can't set both right? You can't design your classifier to balance both false positive rate and positive predictive value if P, which is the underlying proportion of positives in the data, is different. In other words, again in our risk prediction setting, if the number of black defendants is different from the number of white defendants who will be rearrested, right? If those base rates are different, you can't have both types of fairness at once. So one scholar has called this a real-world trolley problem, right? So, trolley problems are often mocked in philosophy as being these sort of weird abstract settings for ethical choices. In this case, the problem is very real. These are both desirable properties, and we can't have both. So, okay, everybody take a deep breath. That's the end of the formalism. We're going to pop out of the formalism, and I'm going to now apply this to 3 different types of areas. The first one being, of course, our classic risk assessment thing. I'm also jumping out from looking at algorithms and formulas to looking at systems in the real world, right? So I've sort of done all of this mathematical work on, I'm at my keyboard, I'm writing this stuff, I'm doing these analyses. Now I'm popping out and I'm saying what's happening in courtrooms, what's happening in the real world. So, as I'm sure all of you thought immediately when I started talking about this stuff, I've been careful with my language. I've been talking about rearrest rather than reoffend. Okay, what we would like to do is predict whether someone will commit a crime. What we observe is whether they're rearrested. We know for certain types of crimes that arrest rates and offense rates are, let's say, loosely coupled, right? So there's not a lot of information there. However, after running around talking to a bunch of people working in this field, there is, whether the relationship or the level of bias between what you can observe and what you care about, the arrest rates and the crime rates, depends very much on when and where and what you ask. There is a long history of debate in terms of how do we interpret police statistics. How are they different in underlying crime rates versus difference in what the police are doing? And then, of course, why is there a difference in underlying crime rates, and how does that relate to histories of oppression and so forth? But if you're going to use risk assessment at all, you have to believe that in some circumstances the data is meaningful, and that goes for all of these scenarios that we're going to look at today. If you can't convince yourself that the proxy you're using has meaning, then you shouldn't be using it at all. Here's another problem. Anti-classification or blinding to a race can actually set you back. So if the data is biased, then knowing the race of the person for whom you have the data can help you make better decisions. That's the problem, right? And so here's a very vivid example from Sandra Mason, who was a public defender in New Orleans. And she says that everybody knew that an arrest meant something different for a black man and a white man. Furthermore, sometimes it's very helpful to transpose these things to sort of less charged settings. So let's talk about rearrest rate versus gender. And you're probably not surprised to hear that women generally reoffend less than men. But if the classifier is blinded to gender, you don't get to know this. And so in fact, in some jurisdictions, Wisconsin in particular, the law says that you have to use different risk assessment tools by gender. And if you have to use different risk assessment tools by gender, why not different risk assessment tools by race? This gets into all kinds of complicated questions. All that I'm trying to say right now is it's not obvious that you should blind your algorithm to protected attributes, even if you could. And then I want to sort of go back to the sort of kerfuffle around ProPublica's story and the fact that these 2 definitions are exclusive, and sort of reframe them. And I'm saying these 2 definitions of fairness can be thought of as definitions from different perspectives. So from the defendant's perspective, you care about false positive rate, right? What is the probability that I'm going to jail? And we can make this formula. Again, we're sort of calculating these things from arrest rates, and the false positive rate is twice as high for black defendants as white defendants. From the judge's perspective, or perhaps the systemic perspective, you are concerned with, well, if this algorithm says they're high risk, what is the probability that they're actually going to be rearrested? Which ends up being different formulas, right? You're using a different set of these numbers to compute this. And North Point and the mid-compass, this was their answer, saying, yeah, but we balanced this thing. It's not that one of these is wrong and the other is right. It's that we have mutually incompatible desirable properties. Okay? Again, we've got a sort of trolley problem. The interests of the stakeholders actually diverge. To make matters worse, even numbers that you might care about, and in fact most of the numbers you might care about, can be gamed. You want there to be a lower false positive rate for black defendants? Fine. Arrest a bunch of black grandmothers who are going to be scored as low risk by the algorithm and also not commit a crime. You can get the false positive rate as low as you like by doing that. So most of these metrics have incentives for the wrong sort of behavior built into them. And finally, there's no guarantee that anybody is going to do what the algorithm says, right? And so, again, we're sort of expanding out so progressively from the algorithm to the layers of the system around it. And this is a big deal. Now, maybe you feel this is a good thing. You know, decisions should be personalized and not based on data, right? There could be attenuating circumstances. How can you send someone to jail without a personalized hearing and so forth? Or maybe you think it's a bad thing. I have to be careful here because I disputed tag. My reading of the evidence that I've been able to find suggests that by and large, judges are ignoring risk scores to the detriment of people who are recommended for release. So here's some data for Kentucky, and the various vertical lines are when various laws and mandates to use various risk assessment tools came in. And you can see that there's an initial jump in release rates followed by a slow decrease sort of closer to the status quo. So they initially get some traction. And this is the justification for the use of risk assessment tools in criminal justice in the first place, is that they're a way to try to jail fewer people pre-trial. The American Constitutional Law Society has a similar analysis for Kentucky. There was just a paper that came out in New York talking about sort of similar ideas. Right? So it's whether humans are going to suspend their own judgment and do just what the algorithm says, or whether humans are going to ignore the judgments and do what they want to do anyway, even if that's already terrible, is an open question. Okay, so I'm now going to transpose it to another case. We've done criminal justice to death. Let's talk about lending. So this is perhaps more relevant to Silicon Valley. We've got this new role of fintech startups who are trying to lend based on things other than the FICO score. So they collect all kinds of other data, perhaps social media data and things that you might not want to be used to make credit decisions. And what they claim is that they can expand access to credit in this way. So the best reference on this is this paper, Predictably Unequal, which is a very general analysis of what happens when you get better prediction in a credit market. And they actually do this in the context of real data, that is to say home mortgage loans from Fannie Mae and Freddie Mac, right? So they have millions of loans, and they analyze the effect of successively better predictors of default. You know, so they build a set of models, each of which is slightly better in terms of accuracy than the previous one. And they look about what happens. And the fundamental insight here is that if your original bad prediction was at all calibrated to the overall level of defaults, like say you know 10% is going to default, and so you have to charge interest that is high enough to cover the 10% default rate. Right? Assuming you were calibrated to begin with, better prediction is going to spread out the rates you charge people while preserving the mean. So it's by definition mean preserving and variance increasing, which means that there's going to be winners and losers. So some people are going to get a higher mortgage rate under better prediction because we know they're riskier. Some people are going to get a lower mortgage rate. So, and in fact, that's what they find on the real data here. They found that in this case, this is an instance where applying an algorithm procedure succeeded in reducing the racial disparity between both acceptance rates and interest rates. However, within a category, so within Hispanic borrowers, some of them were charged way more and some of them were charged way less. So this can cause all sorts of problems, aside from there being some winners and losers. If consider what would happen in an insurance market, right? If we know that certain people are going to be way more expensive for car insurance or health insurance or home theft insurance, then maybe we just don't insure them at all, or maybe they are priced out of the market and they no longer have insurance. So this means that a market which previously succeeded in redistributing risk between people, because we have better prediction, now fails, right? Because the insurance companies will charge them more or decide not to serve them. So better prediction can actually break a market.
Quick question.
Yes.
Could you elaborate on the bottom highlighted observation that the dispersion of rates was greater for Black and Hispanic borrowers than for white and Hispanic borrowers?
Are you asking me why?
Yeah.
Yeah. So first of all, they're talking about within group dispersion. So they're not saying that the rates are higher for Hispanic borrowers than white borrowers. What they're saying is that within Hispanic borrowers, after the prediction accuracy increased, more of them had a higher rate and more of them had a lower rate. And the reason, so you could ask me, why is that dispersion higher? Well, I mean, that's a reflection of the inequalities in society at large, right? More of them are poorer, for example, right? And so that translates in some way, which I'm not entirely clear on, into observable traits in the data, which then allow them to make predictions that cover a wider spread. That's the idea there. So the last case study I'm going to do is one which you may also have heard of. This is call screening for child protective services in Allegheny County, Pennsylvania. This was also in Virginia Eubank's book quite extensively. The source I'm going to use for this is a paper that came out later on the properties of the system they built. And the idea here is that when someone calls Child Protective Services, you sort of have like a CRM, right? You have the history of previous interactions and previous calls and so forth. And you want to predict, based on that previous history, so not the current call, but the previous history, whether this is going to end up being a case where the agency is going to have to intervene in some way, right? So up to and including eventually taking a child away from their parents. So this is very serious stuff, right? This is another case where the stakes are very high. The stakes are always also very high if you miss, right? If there is a serious situation where a child is being harmed and you don't pick it up. So again, false negatives and false positives are both very damaging here. And so why did they build the system at all? Well, one is that better prediction is itself a good because it reduces false positives and false negatives. But another is that they hoped to counter human bias to some extent, right? And in fact, this is a definition of bias by both of the sort of major definitions we talked about earlier. This is both disparate treatment in that cases where black children had lower risk levels than white children, right? They still get screened in. Screened in means flagged for further investigation. And it is disparate impact in that the absolute numbers are higher. So, by any definition, there's some bias here. And so the theory is, well, you can get rid of the disparate treatment bias by ensuring that decisions are based on a risk score. One of the problems that the designers thought about, and so this is also a problem that you've probably seen in predictive policing, is you can get feedback loops. And you will get feedback loops if the thing that you are deciding to do based on the algorithm generates data that the algorithm then uses to tell you to do that thing. So in this case, the algorithm is recommending investigations, but does not use past investigations as data. And that was a deliberate design choice so that you can't get into this situation where someone who has had a previous investigation is then flagged for another investigation, right? So they set that up both in terms of the data the algorithm uses, and they're predicting on an outcome that the users of the tool can't control. And then they did this sort of much more, rather than just sort of false negatives, false positives, they did a much more detailed analysis of the classifiers, where they looked at the false positive versus false negative rate graph. Sort of, those of you who've worked with classifiers will know this as an ROC curve. And the idea here is this sort of tells you what you get if you set a threshold, right? So these little dots are the threshold for the 25% highest risk, right? So you can see that if you set it up so that the people with the in the upper quartile of risk get a mandatory screen in, sort of a mandatory follow-up because the child is thought to be at risk, then you actually end up with different false positive and false negative rates for different races. And again, the underlying reason for that has to do with base rates, right? These groups are not the same. This is the problem we're going to run into over and over again with this stuff, is that people from different groups have different sets of attributes. They have different fundamental base rates of being rearrested, or being qualified for a job, or being a suicide risk, or interventions from Child Protective Services, or whatever it is. As long as there's these underlying differences, you're not going to be able to balance this in all ways. So, and again, the thing that they saw was that humans were sort of ignoring the risk scores. So this x-axis is risk along the bottom. These colors are what happens. So this purple thing, screen in, means they're supposed to flag this case for more follow-up on the idea that the child is at risk. And if you have a score that I think is higher than 15, you're supposed to have a mandatory screen-in, which means that these purple bars should be a lot higher for these two categories, right? So the people using the tool are actually ignoring the policy that was set by the designers. So now there's research ongoing into why do they do this, right? Rather than saying, well, we just need to order them to do the right thing, maybe they know something that we as the tool designers do not. Okay. Everything I've talked about applies whether or not you're using an algorithm. So I want to talk about, so this is the problem. Once you open this can of worms with fairness, you are opening the problem of decisions in general. So this is one viewpoint, which is that you can't have equal predictions in an unequal world, right? If it's really a prediction and the history is unequal, the predictions have to be unequal as well, otherwise it's not actually a prediction. That doesn't mean that you need to jail everyone who's classified as high risk. The key insight here is to separate the prediction from the intervention, right? The prediction is not policy, it's just a prediction. And to ask, why are these unequal? What's different about policing for these two categories? It's not just about observing, okay, why do we have fewer qualified female applicants, or observing that you do. It's about asking that question, why, right? And trying to mess with the algorithm is not going to fix the problem. You may have to look at other parts in this bigger system. Another useful thing when you're sort of trying to figure out, is there an algorithm problem here, is this thought experiment called the Oracle test, which is, okay, never mind the algorithm. What if I had an angel who would tell me the correct answer? Would I still be worried about this stuff? And in the Child Protective Services Screening Agency, maybe you would say yes, right? Yes, we are worried about entering a family into Child Protective Services because that means they're going to undergo greater scrutiny, and they have a much higher probability for future types of bad outcomes that are caused by the intervention that is supposed to help them. So you can also ask about all of these fairness properties for human judges, for example. And human judges don't get to violate the impossibility theorems just because they're humans, right? We cannot build systems, human or algorithmic, which satisfy all of these desirable properties at the same time. We have to make some sort of trade-off. So now that I've convinced you that this is hard and complicated and there are no perfect answers and everything is bad because the whole world is already biased and removing algorithms won't fix it, what do we do? So here in short are the major challenges, right? First of all, the input's never going to be equal, right? So right off the bat, you have to expect some sort of unequal outputs. We're never going to have all of the fairness properties at the same time that we want, so we have some sort of trolley problem. The data is screwed, and we normally don't know exactly how it's screwed. You can't make the algorithm not look at group membership, and it's not clear if you would even want to. Then you've got the humans on top of it, who may slavishly follow a bad algorithm or may ignore a good algorithm, where good and bad are defined relative to the outcomes that you're trying to achieve, right? So engineering the algorithm is only one little part of this. And even if you had perfect prediction, the oracle test, right, you may not get a fair system. This may not be a problem that prediction can solve. So the general rule here is that despite the fact that I've thrown a bunch of math at you, fairness is not a property of the algorithm. It is a property of the system. So you have to ask how this black box fits in the middle of a much larger system and ultimately all of society, including all of the brutal history. There are some useful guideposts for thinking about this and sort of maybe navigating out of this morass. One of which is, rather than sort of talking about sort of abstract qualities of fairness, compare it to the options. Right? Let's make this concrete. What are our choices here? Right? So I've just hopefully convinced you that you can't satisfy some sort of abstract notions of fairness, at least not all of them at the same time. But maybe you can satisfy some of them, and maybe you can do better than the status quo. A more illuminating first question, perhaps, is the reform or the intervention I'm proposing, how does it compare to all of the other interventions I propose, right? So maybe that's the most powerful question, is what are my actual options for intervention here? And finally, we're starting to see legislation around this, and one interesting thing about this legislation is that none of it defines fairness. And the reason none of it defines fairness is because I hope I've convinced you that the fairness properties are highly context-specific. And so it's very hard to make a law which applies to every place where you would use these decision systems. What they do demand is an impact assessment. In other words, what they demand is a written justification for what they did, what properties of fairness they were trying to create by doing that, and why they believed that would succeed. Right? So fairness is less about designing an algorithm or looking for certain quantitative properties in the data, and more about it's closer to legal reasoning, right? You're looking for a justification for what they did in terms of underlying moral, legal, and ethical principles. Okay, that was a huge amount. This is the first time I've tried to put all of this into one talk, so thank you for being my test subjects. If you're confused, it's probably my fault, and I would be happy to chat with any of you afterwards. Thanks.